When researchers measured the heart rate, muscle tension and skin conductance of people before, during and after yawning, they did detect some changes in skin conductance following yawning, indicating a slight increase in physiological activity. However, similar changes occurred when the subjects were asked simply to open their mouths or to breathe deeply. Yawning did nothing special to their state of physiological activity. Experiments have also cast serious doubt on the belief that yawning is triggered by a drop in blood oxygen or a rise in blood carbon dioxide. Volunteers were told to think about yawning while they breathed either normal air, pure oxygen, or an air mixture with an above normal level of carbon dioxide. If the theory was correct, breathing air with extra carbon dioxide should have triggered yawning, while breathing pure oxygen should have suppressed yawning. In fact, neither condition made any difference to the frequency of yawning, which remained constant at about 24 yawns per hour. Another experiment demonstrated that physical exercise, which was sufficiently vigorous to double the rate of breathing, had no effect on the frequency of yawning. Again, the implication is that yawning has little or nothing to do with oxygen. A completely different theory holds that yawning assists in the physical development of the lungs early in life, but has no remaining biological function in adults. It has been suggested that yawning and hiccuping might serve to clear out the fetus's airways. The lungs of a fetus secrete a liquid that mixes with its mother's amniotic fluid. Babies with congenital blockages that prevent this fluid from escaping from their lungs are sometimes born with deformed lungs. It might be that yawning helps to clear out the lungs by periodically lowering the pressure in them. According to this theory, yawning in adults is just a developmental fossil with no biological function. But, while accepting that not everything in life can be explained by Darwinian evolution, there are sound reasons for being skeptical of theories like this one, which avoid the issue of what yawning does for adults. Yawning is distracting, consumes energy and takes time. It is almost certainly doing something significant in adults as well as in fetuses. What could it be? The empirical evidence, such as it is, suggests an altogether different function for yawning, namely, that yawning prepares us for a change in activity level. Support for this theory came from a study of yawning behavior in everyday life. Volunteers wore wrist-mounted devices that automatically recorded their physical activity for up to 2 weeks. The volunteers also recorded their yawns by pressing a button on the device each time they yawned. The data showed that yawning tended to occur about 15 minutes before a period of increased behavioral activity. Yawning bore no relationship to sleep patterns, however. This accords with anecdotal evidence that people often yawn in situations where they are neither tired nor bored, but are preparing for impending mental and physical activity. Such yawning is often referred to as incongruous because it seems out of place, at least on the tiredness view. Soldiers yawning before combat, musicians yawning before performing, and athletes yawning before competing. Their yawning seems to have nothing to do with sleepiness or boredom, quite the reverse, but it does precede a change in activity level. TPO 18 Passage 3. Lightning. Lightning is a brilliant flash of light produced by an electrical discharge from a storm cloud. The electrical discharge takes place when the attractive tension between a region of negatively charged particles and a region of positively charged particles becomes so great that the charged particles suddenly rush together. The coming together of the oppositely charged particles neutralizes the electrical tension and releases a tremendous amount of energy, which we see as lightning. The separation of positively and negatively charged particles takes place during the development of the storm cloud. The separation of charged particles that forms in a storm cloud has a sandwich-like structure. Concentrations of positively charged particles develop at the top and bottom of the cloud, but the middle region becomes negatively charged. Recent measurements made in the field together with laboratory simulations offer a promising explanation of how this structure of charged particles forms. What happens is that small pellets of ice form in the cold upper regions of the cloud. When these ice pellets fall, some of them strike much smaller ice crystals in the center of the cloud. The temperature at the center of the cloud is about -15 degrees Celsius or lower. At such temperatures, the collision between the ice pellets and the ice crystals causes electrical charges to shift so that the ice pellets acquire a negative charge and the ice crystals become positively charged. Then updraft wind currents carry the light, positively charged ice crystals up to the top of the cloud. The heavier negatively charged ice pellets are left to concentrate in the center. This process explains why the top of the cloud becomes positively charged, while the center becomes negatively charged. The negatively charged region is large, several hundred meters thick and several kilometers in diameter. Below this large, cold, negatively charged region, the cloud is warmer than 5 degrees Celsius, and at these temperatures, collisions between ice crystals and falling ice pellets produce positively charged ice pellets that then populate a small region at the base of the cloud. Most lightning takes place within a cloud when the charge separation within the cloud collapses. However, as the storm cloud develops, the ground beneath the cloud becomes positively charged and lightning can take place in the form of an electrical discharge between the negative charge of the cloud and the positively charged ground. Lightning that strikes the ground is the most likely to be destructive, so even though it represents only 20% of all lightning, it has received a lot of scientific attention. Using high-speed photography, scientists have determined that there are 2 steps to the occurrence of lightning from a cloud to the ground. First, a channel, or path, is formed that connects the cloud and the ground. Then a strong current of electrons follows that path from the cloud to the ground, and it is that current that illuminates the channel as the lightning we see. The formation of the channel is initiated when electrons surge from the cloud base toward the ground. When a stream of these negatively charged electrons comes within 100 meters of the ground, it is met by a stream of positively charged particles that comes up from the ground. When the negatively and positively charged streams meet, a complete channel connecting the cloud and the ground is formed. The channel is only a few centimeters in diameter, but that is wide enough for electrons to follow the channel to the ground in the visible form of a flash of lightning. The stream of positive particles that meets the surge of electrons from the cloud often arises from a tall pointed structure such as a metal flagpole or a tower. That is why the subsequent lightning that follows the completed channel often strikes a tall structure. Once a channel has been formed, it is usually used by several lightning discharges, each of them consisting of a stream of electrons from the cloud meeting a stream of positive particles along the established path. Sometimes, however, a stream of electrons following an established channel is met by a positive stream making a new path up from the ground. The result is a forked lightning that strikes the ground in 2 places. TPO-19. TPO-19 Passage 1. The Roman army's impact on Britain. In the wake of the Roman Empire's conquest of Britain in the 1st century AD, a large number of troops stayed in the new province, and these troops had a considerable impact on Britain with their camps, fortifications, and participation in the local economy. Assessing the impact of the army on the civilian population starts from the realization that the soldiers were always unevenly distributed across the country. Areas rapidly incorporated into the empire were not long affected by the military. Where the army remained stationed, its presence was much more influential. The imposition of a military base involved the requisition of native lands for both the fort and the territory needed to feed and exercise the soldiers' animals. The imposition of military rule also robbed local leaders of opportunities to participate in local government, so social development was stunted and the seeds of disaffection sown. This then meant that the military had to remain to suppress rebellion and organize government. Economic exchange was clearly very important as the Roman army brought with it very substantial spending power. Locally, a fort had 2 kinds of impact. Its large population needed food and other supplies. Some of these were certainly brought from long distances, but demands were inevitably placed on the local area. Although goods could be requisitioned, they were usually paid for, and this probably stimulated changes in the local economy. When not campaigning, soldiers needed to be occupied, otherwise they represented a potentially dangerous source of friction and disloyalty. Hence a writing tablet dated April 25 tells of 343 men at one fort engaged on tasks like shoemaking, building a bathhouse, operating kilns, digging clay, and working lead. Such activities had a major effect on the local area, in particular with the construction of infrastructure such as roads, which improved access to remote areas. Each soldier received his pay, but in regions without a developed economy there was initially little on which it could be spent. The pool of excess cash rapidly stimulated a thriving economy outside fort gates. Some of the demand for the services and goods was no doubt fulfilled by people drawn from far afield, but some local people certainly became entwined in this new economy. There was informal marriage with soldiers, who until AD 197 were not legally entitled to wed, and whole new communities grew up near the forts. These settlements acted like small towns, becoming centers for the artisan and trading populations. The army also provided a means of personal advancement for auxiliary soldiers recruited from the native peoples, as a man obtained hereditary Roman citizenship on retirement after service in an auxiliary regiment. Such units recruited on an ad hoc basis from the area in which they were stationed, and through a civilian large-scale recruitment within Britain. The total numbers were at least 12,500 men up to the reign of the Emperor Hadrian, with a peak around AD 80. Although a small proportion of the total population, this perhaps had a massive local impact when a large proportion of the young men were removed from an area. Newly raised regiments were normally transferred to another province from whence it was unlikely that individual recruits would ever return. Most units raised in Britain went elsewhere on the European continent, although one is recorded in Morocco. The reverse process brought young men to Britain, where many continued to live after their 20 to 25 years of service, and this added to the cosmopolitan Roman character of the frontier population. By the later Roman period, frontier garrisons were only rarely transferred, service in units became effectively hereditary, and forts were no longer populated or maintained at full strength. This process of settling in as a community over several generations, combined with local recruitment, presumably accounts for the apparent stability of the British northern frontier in the later Roman period. It also explains why some of the forts continued in occupation long after Rome ceased to have any formal authority in Britain, at the beginning of the 5th century AD. The circumstances that had allowed natives to become Romanized also led the self-sustaining military community of the frontier area to become effectively British. TPO 19 Passage 2. Succession, Climax, and Ecosystems. In the late 19th century, ecology began to grow into an independent science from its roots in natural history and plant geography. The emphasis of this new community ecology was on the composition and structure of communities consisting of different species. In the early 20th century, the American ecologist Frederick Clements pointed out that a succession of plant communities would develop after a disturbance such as a volcanic eruption, heavy flood, or forest fire. An abandoned field, for instance, will be invaded successively by herbaceous plants, shrubs, and trees, eventually becoming a forest. Light-loving species are always among the first invaders, while shade-tolerant species appear later in the succession. Clements and other early ecologists saw almost law-like regularity in the order of succession, but that has not been substantiated. A general trend can be recognized, but the details are usually unpredictable. Succession is influenced by many factors: the nature of the soil, exposure to sun and wind, regularity of precipitation, chance colonizations, and many other random processes. The final stage of a succession, called the climax by Clements and early ecologists, is likewise not predictable or of uniform composition. There is usually a good deal of turnover in species composition, even in a mature community. The nature of the climax is influenced by the same factors that influenced succession. Nevertheless, mature natural environments are usually in equilibrium. They change relatively little through time unless the environment itself changes. For Clements, the climax was a superorganism, an organic entity. Even some authors who accepted the climax concept rejected Clements' characterization of it as a superorganism, and it is indeed a misleading metaphor. An ant colony may be legitimately called a superorganism because its communication system is so highly organized that the colony always works as a whole and appropriately according to the circumstances. But there is no evidence for such an interacting communicative network in a climax plant formation. Many authors prefer the term association to the term community in order to stress the looseness of the interaction. Even less fortunate was the extension of this type of thinking to include animals as well as plants. This resulted in the biome, a combination of coexisting flora and fauna. Though it is true that many animals are strictly associated with certain plants, it is misleading to speak of a spruce moose biome, for example, because there is no internal cohesion to their association as in an organism. The spruce community is not substantially affected by either the presence or absence of moose. Indeed, there are vast areas of spruce forest without moose. The opposition to the Clementsian concept of plant ecology was initiated by Herbert Gleason, soon joined by various other ecologists. Their major point was that the distribution of a given species was controlled by the habitat requirements of that species and that therefore the vegetation types were a simple consequence of the ecologies of individual plant species. With climax, biome, superorganism, and various other technical terms for the association of animals and plants at a given locality being criticized, the term ecosystem was more and more widely adopted for the whole system of associated organisms together with the physical factors of their environment. Eventually, the energy-transforming role of such a system was emphasized. Ecosystems thus involve the circulation, transformation, and accumulation of energy and matter through the medium of living things and their activities. The ecologist is concerned primarily with the quantities of matter and energy that pass through a given ecosystem and with the rates at which they do so. Although the ecosystem concept was very popular in the 1950s and 1960s, it is no longer the dominant paradigm. Gleason's arguments against climax and biome are largely valid against ecosystems as well. Furthermore, the number of interactions is so great that they are difficult to analyze, even with the help of large computers. Finally, younger ecologists have found ecological problems involving behavior and life history adaptations more attractive than measuring physical constants. Nevertheless, one still speaks of the ecosystem when referring to a local association of animals and plants, usually without paying much attention to the energy aspects. TPO 19 Passage 3. Discovering the Ice Ages. In the middle of the 19th century, Louis Agassiz, one of the first scientists to study glaciers, immigrated to the United States from Switzerland and became a professor at Harvard University, where he continued his studies in geology and other sciences. For his research, Agassiz visited many places in the northern parts of Europe and North America, from the mountains of Scandinavia and New England to the rolling hills of the American Midwest. In all these diverse regions, Agassiz saw signs of glacial erosion and sedimentation. In flat plains country, he saw moraines that reminded him of the terminal moraines found at the end of valley glaciers in the Alps. The heterogeneous material of the drift convinced him of its glacial origin. The areas covered by this material were so vast that the ice that deposited it must have been a continental glacier larger than Greenland or Antarctica. Eventually, Agassiz and others convinced geologists and the general public that a great continental glaciation had extended the polar ice caps far into regions that now enjoy temperate climates. For the first time, people began to talk about ice ages. It was also apparent that the glaciation occurred in the relatively recent past because the drift was soft, like freshly deposited sediment. We now know the age of the glaciation accurately from radiometric dating of the carbon-14 in logs buried in the drift. The drift of the last glaciation was deposited during one of the most recent epochs of geologic time, the Pleistocene, which lasted from 1.8 million to 10,000 years ago. Along the east coast of the United States, the southernmost advance of this ice is recorded by the enormous sand and drift deposits of the terminal moraines that form Long Island and Cape Cod. It soon became clear that there were multiple glacial ages during the Pleistocene, with warmer interglacial intervals between them. As geologists mapped glacial deposits in the late 19th century, they became aware that there were several layers of drift, the lower ones corresponding to earlier ice ages. Between the older layers of glacial material were well-developed soils containing fossils of warm climate plants. These soils were evidence that the glaciers retreated as the climate warmed. By the early part of the 20th century, scientists believed that 4 distinct glaciations had affected North America and Europe during the Pleistocene epoch. This idea was modified in the late 20th century, when geologists and oceanographers examining oceanic sediment found fossil evidence of warming and cooling of the oceans. Ocean sediments presented a much more complete geologic record of the Pleistocene than continental glacial deposits did. The fossils buried in Pleistocene and earlier ocean sediments were of foraminifera, small, single-celled marine organisms that secrete shells of calcium carbonate, or calcite. These shells differ in their proportion of ordinary oxygen and the heavy oxygen isotope. The ratio of oxygen-16 to oxygen-18 found in the calcite of a foraminiferous shell depends on the temperature of the water in which the organism lived. Different ratios in the shells preserved in various layers of sediment reveal the temperature changes in the oceans during the Pleistocene epoch. Isotopic analysis of shells allowed geologists to measure another glacial effect. They could trace the growth and shrinkage of continental glaciers, even in parts of the ocean where there may have been no great change in temperature, around the equator, for example. The oxygen isotope ratio of the ocean changes as a great deal of water is withdrawn from it by evaporation and is precipitated as snow to form glacial ice. During glaciations, the lighter oxygen-16 has a greater tendency to evaporate from the ocean surface than the heavier oxygen-18 does. Thus, more of the heavy isotope is left behind in the ocean and absorbed by marine organisms. From this analysis of marine sediments, geologists have learned that there were many shorter, more regular cycles of glaciation and deglaciation than geologists had recognized from the glacial drift of the continents alone. TPO-20 TPO-20 Passage 1 Westward Migration. The story of the westward movement of population in the United States is, in the main, the story of the expansion of American agriculture, of the development of new areas for the raising of livestock and the cultivation of wheat, corn, tobacco, and cotton. After 1815, improved transportation enabled more and more Western farmers to escape a self-sufficient way of life and enter a national market economy. During periods when commodity prices were high, the rate of westward migration increased spectacularly. Old America seemed to be breaking up and moving westward, observed an English visitor in 1817, during the first great wave of migration. Emigration to the west reached a peak in the 1830s. Whereas in 1810 only a seventh of the American people lived west of the Appalachian Mountains, by 1840 more than a third lived there. Why were these hundreds of thousands of settlers, most of them farmers, some of them artisans, drawn away from the cleared fields and established cities and villages of the East? Certain characteristics of American society help to explain this remarkable migration. The European ancestors of some Americans had for centuries lived rooted to the same village or piece of land until some religious, political, or economic crisis uprooted them and drove them across the Atlantic. Many of those who experienced this sharp break thereafter lacked the ties that had bound them and their ancestors to a single place. Moreover, European society was relatively stratified, occupation and social status were inherited. In American society, however, the class structure was less rigid. Some people changed occupations easily and believed it was their duty to improve their social and economic position. As a result, many Americans were inveterately restless, rootless, and ambitious people. Therefore, these social traits helped to produce the nomadic and daring settlers who kept pushing westward beyond the fringes of settlement. In addition, there were other immigrants who migrated west in search of new homes, material success, and better lives. The West had plenty of attractions: the alluvial river bottoms, the fecund soils of the rolling forest lands, the black loams of the prairies were tempting to New England farmers working their rocky, sterile land, and to southeastern farmers plagued with soil depletion and erosion. In 1820, under a new land law, a farm could be bought for $100. The continued proliferation of banks made it easier for those without cash to negotiate loans in paper money. Western farmers borrowed with the confident expectation that the expanding economy would keep farm prices high, thus making it easy to repay loans when they fell due. Transportation was becoming less of a problem for those who wished to move west and for those who had farm surpluses to send to market. Prior to 1815, Western farmers who did not live on navigable waterways were connected to them only by dirt roads and mountain trails. Livestock could be driven across the mountains, but the cost of transporting bulky grains in this fashion was several times greater than their value in eastern markets. The first step toward an improvement of Western transportation was the construction of turnpikes. These roads made possible a reduction in transportation costs, and thus stimulated the commercialization of agriculture along their routes. Two other developments presaged the end of the era of turnpikes and started a transportation revolution that resulted in increased regional specialization and the growth of a national market economy. First came the steamboat, although flatboats and keelboats continued to be important until the 1850s. Steamboats eventually superseded all other craft in the carrying of passengers and freight. Steamboats were not only faster but also transported upriver freight for about 1/10 of what it had previously cost on hand-propelled keelboats. Next came the Erie Canal, an enormous project in its day, spanning about 350 miles. After the canal went into operation, the cost per mile of transporting a ton of freight from Buffalo to New York City declined from nearly 20 cents to less than 1 cent. Eventually, the western states diverted much of their produce from the rivers to the Erie Canal, a shorter route to eastern markets. TPO 20 Passage 2. Early settlements in the Southwest Asia. The universal global warming at the end of the Ice Age had dramatic effects on temperate regions of Asia, Europe, and North America. Ice sheets retreated and sea levels rose. The climatic changes in southwestern Asia were more subtle, in that they involved shifts in mountain snowlines, rainfall patterns, and vegetation cover. However, these same cycles of change had momentous impacts on the sparse human populations of the region. At the end of the Ice Age, no more than a few thousand foragers lived along the eastern Mediterranean coast, in the Jordan and Euphrates valleys. Within 2,000 years, the human population of the region numbered in the tens of thousands, all as a result of village life and farming. Thanks to new environmental and archaeological discoveries, we now know something about this remarkable change in local life. Pollen samples from freshwater lakes in Syria and elsewhere tell us forest cover expanded rapidly at the end of the Ice Age, for the southwestern Asian climate was still cooler and considerably wetter than today. Many areas were richer in animal and plant species than they are now, making them highly favorable for human occupation. About 9000 BC, most human settlements lay in the area along the Mediterranean coast and in the Zagros Mountains of Iran and their foothills. Some local areas, like the Jordan River Valley, the Middle Euphrates Valley, and some Zagros valleys, were more densely populated than elsewhere. Here more sedentary and more complex societies flourished. These people exploited the landscape intensively, foraging on hill slopes for wild cereal grasses and nuts, while hunting gazelle and other game on grassy lowlands and in river valleys. Their settlements contain exotic objects such as seashells, stone bowls, and artifacts made of obsidian, all traded from afar. This considerable volume of inter-community exchange brought a degree of social complexity in its wake. Thanks to extremely fine-grained excavation and extensive use of flotation methods, we know a great deal about the foraging practices of the inhabitants of Abu Huraira in Syria's Euphrates Valley. Abu Huraira was founded about 9500 BC, a small village settlement of cramped pit dwellings with reed roofs supported by wooden uprights. For the next 1,500 years, its inhabitants enjoyed a somewhat warmer and damper climate than today, living in a well-wooded steppe area where wild cereal grasses were abundant. They subsisted off spring migrations of Persian gazelles from the south. With such a favorable location, about 300 to 400 people lived in a sizable, permanent settlement. They were no longer a series of small bands but lived in a large community with more elaborate social organization, probably grouped into clans of people of common descent. The flotation samples from the excavations allowed botanists to study shifts in plant collecting habits as if they were looking through a telescope at a changing landscape. Hundreds of tiny plant remains show how the inhabitants exploited nut harvests in nearby pistachio and oak forests. However, as the climate dried up, the forests retreated from the vicinity of the settlement. The inhabitants turned to wild cereal grasses instead, collecting them by the thousands, while the percentage of nuts in the diet fell. By 8200 BC, drought conditions were so severe that the people abandoned their long-established settlement, perhaps dispersing into smaller camps. 5 centuries later, about 7700 BC, a new village rose on the mound. At first the inhabitants still hunted gazelle intensively. Then, about 7000 BC, within the space of a few generations, they switched abruptly to herding domesticated goats and sheep and to growing einkorn, pulses, and other cereal grasses. Abu Huraira grew rapidly until it covered nearly 30 acres. It was a close-knit community of rectangular, one-story mud brick houses, joined by narrow lanes and courtyards, finally abandoned about 5000 BC. Many complex factors led to the adoption of the new economies, not only at Abu Huraira, but at many other locations such as Ain Ghazal, also in Syria, where goat toe bones showing the telltale marks of abrasion caused by foot tethering testify to early herding of domestic stock. TPO 20 Passage 3. Fossil preservation. When one considers the many ways by which organisms are completely destroyed after death, it is remarkable that fossils are as common as they are. Attack by scavengers and bacteria, chemical decay, and destruction by erosion and other geologic agencies make the odds against preservation very high. However, the chances of escaping complete destruction are vastly improved if the organism happens to have a mineralized skeleton and dies in a place where it can be quickly buried by sediment. Both of these conditions are often found on the ocean floors, where shelled invertebrates flourish and are covered by the continuous rain of sedimentary particles. Although most fossils are found in marine sedimentary rocks, they also are found in terrestrial deposits left by streams and lakes. On occasion, animals and plants have been preserved after becoming immersed in tar or quicksand, trapped in ice or lava flows, or engulfed by rapid falls of volcanic ash. The term fossil often implies petrifaction, literally a transformation into stone. After the death of an organism, the soft tissue is ordinarily consumed by scavengers and bacteria. The empty shell of a snail or clam may be left behind, and if it is sufficiently durable and resistant to dissolution, it may remain basically unchanged for a long period of time. Indeed, unaltered shells of marine invertebrates are known from deposits over 100 million years old. In many marine creatures, however, the skeleton is composed of a mineral variety of calcium carbonate called aragonite. Although aragonite has the same composition as the more familiar mineral known as calcite, it has a different crystal form, is relatively unstable, and in time changes to the more stable calcite. Many other processes may alter the shell of a clam or snail and enhance its chances for preservation. Water containing dissolved silica, calcium carbonate, or iron may circulate through the enclosing sediment and be deposited in cavities such as marrow cavities and canals in bone once occupied by blood vessels and nerves. In such cases, the original composition of the bone or shell remains, but the fossil is made harder and more durable. This addition of a chemically precipitated substance into pore spaces is termed permineralization. Petrifaction may also involve a simultaneous exchange of the original substance of a dead plant or animal with mineral matter of a different composition. This process is termed replacement because solutions have dissolved the original material and replaced it with an equal volume of the new substance. Replacement can be a marvelously precise process so that details of shell ornamentation, tree rings in wood, and delicate structures in bone are accurately preserved. Another type of fossilization, known as carbonization, occurs when soft tissues are preserved as thin films of carbon. Leaves and tissue of soft-bodied organisms such as jellyfish or worms may accumulate, become buried and compressed, and lose their volatile constituents. The carbon often remains behind as a blackened silhouette. Although it is certainly true that the possession of hard parts enhances the prospect of preservation, organisms having soft tissues and organs are also occasionally preserved. Insects and even small invertebrates have been found preserved in the hardened resins of conifers and certain other trees. X-ray examination of thin slabs of rock sometimes reveals the ghostly outlines of tentacles, digestive tracts, and visual organs of a variety of marine creatures. Soft parts, including skin, hair, and viscera of Ice Age mammoths, have been preserved in frozen soil or in the oozing tar of oil seeps. The probability that actual remains of soft tissue will be preserved is improved if the organism dies in an environment of rapid deposition and oxygen deprivation. Under such conditions, the destructive effects of bacteria are diminished. The Middle Eocene Messel shale of Germany accumulated in such an environment. The shale was deposited in an oxygen-deficient lake where lethal gases sometimes bubbled up and killed animals. Their remains accumulated on the floor of the lake and were then covered by clay and silt. Among the superbly preserved messel fossils are insects with iridescent exoskeletons, frogs with skin and blood vessels intact, and even entire small mammals with preserved fur and soft tissue.
TPO-21. TPO-21 Passage 1. Geothermal energy. Earth's internal heat, fueled by radioactivity, provides the energy for plate tectonics and continental drift, mountain building, and earthquakes. It can also be harnessed to drive electric generators and heat homes.
Geothermal energy becomes available in a practical form when underground heat is transferred by water that is heated as it passes through a subsurface region of hot rocks that may be hundreds or thousands of feet deep. The water is usually naturally occurring groundwater that seeps down along fractures in the rock. Less typically, the water is artificially introduced by being pumped down from the surface. The water is brought to the surface, as a liquid or steam, through holes drilled for the purpose. By far the most abundant form of geothermal energy occurs at the relatively low temperatures of 80 degrees to 180 degrees centigrade. Water circulated through heat reservoirs in this temperature range is able to extract enough heat to warm residential, commercial, and industrial spaces. More than 20,000 apartments in France are now heated by warm underground water drawn from a heat reservoir in a geologic structure near Paris called the Paris Basin. Iceland sits on a volcanic structure known as the Mid-Atlantic Ridge. Reykjavik, the capital of Iceland, is entirely heated by geothermal energy derived from volcanic heat. Geothermal reservoirs with temperatures above 180 degrees centigrade are useful for generating electricity. They occur primarily in regions of recent volcanic activity as hot, dry rock, natural hot water, or natural steam. The latter two sources are limited to those few areas where surface water seeps down through underground faults or fractures to reach deep rocks heated by the recent activity of molten rock material. The world's largest supply of natural steam occurs at the geysers, 120 kilometers north of San Francisco, California. In the 1990s, enough electricity to meet about half the needs of San Francisco was being generated there. This facility was then in its third decade of production and was beginning to show signs of decline, perhaps because of overdevelopment. By the late 1990s, some 70 geothermal electric generating plants were in operation in California, Utah, Nevada, and Hawaii, generating enough power to supply about 1 million people. 18 countries now generate electricity using geothermal heat. Extracting heat from very hot, dry rocks presents a more difficult problem. The rocks must be fractured to permit the circulation of water, and the water must be provided artificially. The rocks are fractured by water pumped down at very high pressures. Experiments are underway to develop technologies for exploiting this resource. Like most other energy sources, geothermal energy presents some environmental problems. The surface of the ground can sink if hot groundwater is withdrawn without being replaced. In addition, water heated geothermally can contain salts and toxic materials dissolved from the hot rock. These waters present a disposal problem if they are not returned to the ground from which they were removed. The contribution of geothermal energy to the world's energy future is difficult to estimate. Geothermal energy is in a sense not renewable, because in most cases the heat would be drawn out of a reservoir much more rapidly than it would be replaced by the very slow geological processes by which heat flows through solid rock into a heat reservoir. However, in many places the resource is potentially so large that its future will depend on the economics of production. At present, we can make efficient use of only naturally occurring hot water or steam deposits. Although the potential is enormous, it is likely that in the near future geothermal energy can make important local contributions only where the resource is close to the user and the economics are favorable, as they are in California, New Zealand, and Iceland. Geothermal energy probably will not make large-scale contributions to the world energy budget until well into the 21st century, if ever. TPO-21 Passage 2. The origins of agriculture. How did it come about that farming developed independently in a number of world centers at more or less the same time? Agriculture developed slowly among populations that had an extensive knowledge of plants and animals. Changing from hunting and gathering to agriculture had no immediate advantages. To start with, it forced the population to abandon the nomad's life and became sedentary, to develop methods of storage and, often, systems of irrigation. While hunter-gatherers always had the option of moving elsewhere when the resources were exhausted, this became more difficult with farming. Furthermore, as the archaeological record shows, the state of health of agriculturalists was worse than that of their contemporary hunter-gatherers. Traditionally, it was believed that the transition to agriculture was the result of a worldwide population crisis. It was argued that once hunter-gatherers had occupied the whole world, the population started to grow everywhere and food became scarce. Agriculture would have been a solution to this problem. We know, however, that contemporary hunter-gatherer societies control their population in a variety of ways. The idea of a world population crisis is therefore unlikely, although population pressure might have arisen in some areas. Climatic changes at the end of the glacial period 13,000 years ago have been proposed to account for the emergence of farming. The temperature increased dramatically in a short period of time, allowing for a growth of the hunting-gathering population due to the abundance of resources. There were, however, fluctuations in climatic conditions, with the consequences that wet conditions were followed by dry ones, so that the availability of plants and animals oscillated brusquely. It would appear that the instability of the climatic conditions led populations that had originally been nomadic to settle down and develop a sedentary style of life, which led in turn to population growth and to the need to increase the amount of food available. Farming originated in these conditions. Later on, it became very difficult to change because of the significant expansion of these populations. It could be argued, however, that these conditions are not sufficient to explain the origins of agriculture. Earth had experienced previous periods of climatic change, and yet agriculture had not been developed. It is archaeologist Stephen Mithen's thesis, brilliantly developed in his book The Prehistory of the Mind, that approximately 40,000 years ago the human mind developed cognitive fluidity, that is, the integration of the specializations of the mind: technical, natural history, social intelligence, and the linguistic capacity. Cognitive fluidity explains the appearance of art, religion, and sophisticated speech. Once humans possessed such a mind, they were able to find an imaginative solution to a situation of severe economic crisis such as the farming dilemma described earlier. Mithen proposes the existence of four mental elements to account for the emergence of farming: the ability to develop tools that could be used intensively to harvest and process plant resources, the tendency to use plants and animals as the medium to acquire social prestige and power, the tendency to develop social relationships with animals structurally similar to those developed with people, specifically, the ability to think of animals as people and of people as animals, and the tendency to manipulate plants and animals. The fact that some societies domesticated animals and plants, discovered the use of metal tools, became literate, and developed a state should not make us forget that others developed pastoralism or horticulture but remained illiterate and at low levels of productivity. A few entered the modern period as hunting and gathering societies. It is anthropologically important to inquire into the conditions that made some societies adopt agriculture while others remained hunter-gatherers or horticulturalists. However, it should be kept in mind that many societies that knew of agriculture more or less consciously avoided it. Whether Mithen's explanation is satisfactory is open to contention, and some authors have recently emphasized the importance of other factors. TPO 21 Passage 3. Autobiographical memory. Think back to your childhood and try to identify your earliest memory. How old were you? Most people are not able to recount memories for experiences prior to the age of 3 years, a phenomenon called infantile amnesia. The question of why infantile amnesia occurs has intrigued psychologists for decades, especially in light of ample evidence that infants and young children can display impressive memory capabilities. Many find that understanding the general nature of autobiographical memory, that is, memory for events that have occurred in one's own life, can provide some important clues to this mystery. Between ages 3 and 4, children begin to give fairly lengthy and cohesive descriptions of events in their past. What factors are responsible for this developmental turning point? Perhaps the explanation goes back to some ideas raised by influential Swiss psychologist Jean Piaget, namely, that children under age 2 years represent events in a qualitatively different form than older children do. According to this line of thought, the verbal abilities that blossom in the 2-year-old allow events to be coded in a form radically different from the action-based codes of the infant. Verbal abilities of 1-year-olds are, in fact, related to their memories for events 1 year later. When researchers had 1-year-olds imitate an action sequence 1 year after they first saw it, there was correlation between the children's verbal skills at the time they first saw the event and their success on the later memory task. However, even children with low verbal skills showed evidence of remembering the event. Thus, memories may be facilitated by but are not dependent on those verbal skills. Another suggestion is that before children can talk about past events in their lives, they need to have a reasonable understanding of the self as a psychological entity. The development of an understanding of the self becomes evident between the first and second years of life and shows rapid elaboration in subsequent years. The realization that the physical self has continuity in time, according to this hypothesis, lays the foundation for the emergence of autobiographical memory. A third possibility is that children will not be able to tell their own life story until they understand something about the general form stories take, that is, the structure of narratives. Knowledge about narratives arises from social interactions, particularly the storytelling that children experience from parents and the attempts parents make to talk with children about past events in their lives. When parents talk with children about what we did today or last week or last year, they guide the children's formation of a framework for talking about the past. They also provide children with reminders about the memory and relay the message that memories are valued as part of the cultural experience. It is interesting to note that some studies show Caucasian American children have earlier childhood memories than Korean children do. Furthermore, other studies show that Caucasian American mother-child pairs talk about past events 3 times more often than do Korean mother-child pairs. Thus, the types of social experiences children have do factor into the development of autobiographical memories. A final suggestion is that children must begin to develop a theory of mind and awareness of the concept of mental states, their own and those of others, before they can talk about their own past memories. Once children become capable of answering such questions as, what does it mean to remember, and what does it mean to know something, improvements in memory seem to occur. It may be that the developments just described are intertwined with and influence one another. Talking with parents about the past may enhance the development of the self-concept, for example, as well as help the child understand what it means to remember. No doubt the ability to talk about one's past represents memory of a different level of complexity than simple recognition or recall. TPO 22. TPO 22 Passage 1. Spartina. Spartina alterniflora, known as cordgrass, is a deciduous, perennial flowering plant native to the Atlantic coast and the Gulf Coast of the United States. It is the dominant native species of the lower salt marshes along these coasts, where it grows in the intertidal zone. These natural salt marshes are among the most productive habitats in the marine environment. Nutrient-rich water is brought to the wetlands during each high tide, making a high rate of food production possible. As the seaweed and marsh grass leaves die, bacteria break down the plant material, and insects, small shrimp-like organisms, fiddler crabs, and marsh snails eat the decaying plant tissue, digest it, and excrete wastes high in nutrients. Numerous insects occupy the marsh, feeding on living or dead cordgrass tissue, and red-winged blackbirds, sparrows, rodents, rabbits, and deer feed directly on the cordgrass. Each tidal cycle carries plant material into the offshore water to be used by the subtidal organisms. Spartina is an exceedingly competitive plant. It spreads primarily by underground stems. Colonies form when pieces of the root system or whole plants float into an area and take root, or when seeds float into a suitable area and germinate. Spartina establishes itself on substrates ranging from sand and silt to gravel and cobble and is tolerant of salinities ranging from that of near freshwater to that of saltwater. Because they lack oxygen, marsh sediments are high in sulfides that are toxic to most plants. Spartina has the ability to take up sulfides and convert them to sulfate, a form of sulfur that the plant can use. This ability makes it easier for the grass to colonize marsh environments. Another adaptive advantage is Spartina's ability to use carbon dioxide more efficiently than most other plants. These characteristics make Spartina a valuable component of the estuaries where it occurs naturally. The plant functions as a stabilizer and a sediment trap and as a nursery area for estuarine fish and shellfish. Once established, a stand of Spartina begins to trap sediment, changing the substrate elevation, and eventually the stand evolves into a high marsh system where Spartina is gradually displaced by higher elevation, brackish water species. As elevation increases, narrow, deep channels of water form throughout the marsh. Along the east coast, Spartina is considered valuable for its ability to prevent erosion and marshland deterioration. It is also used for coastal restoration projects and the creation of new wetland sites. Spartina was transported to Washington state in packing materials for oysters transplanted from the East Coast in 1894. Leaving its insect predators behind, the cordgrass has been spreading slowly and steadily along Washington's tidal estuaries on the West Coast, crowding out the native plants and drastically altering the landscape by trapping sediment. Spartina modifies tidal mudflats, turning them into high marshes inhospitable to the many fish and waterfowl that depend on the mudflats. It is already hampering the oyster harvest and the Dungeness crab fishery, and it interferes with the recreational use of beaches and waterfronts. Spartina has been transplanted to England and to New Zealand for land reclamation and shoreline stabilization. In New Zealand, the plant has spread rapidly, changing mudflats with marshy fringes to extensive salt meadows and reducing the number and kinds of birds and animals that use the marsh. Efforts to control Spartina outside its natural environment have included burning, flooding, shading plants with black canvas or plastic, smothering the plants with dredged materials or clay, applying herbicide, and mowing repeatedly. Little success has been reported in New Zealand and England. Washington State's management program has tried many of these methods and is presently using the herbicide glyphosate to control its spread. Work has begun to determine the feasibility of using insects as biological controls, but effective biological controls are considered years away. Even with a massive effort, it is doubtful that complete eradication of Spartina from non-native habitats is possible, for it has become an integral part of these shorelines and estuaries during the last 100 to 200 years. TPO 22 Passage 2. The birth of photography. Perceptions of the visible world were greatly altered by the invention of photography in the middle of the 19th century. In particular, and quite logically, the art of painting was forever changed, though not always in the ways one might have expected. The realistic and naturalistic painters of the mid and late 19th century were all intently aware of photography as a thing to use, to learn from, and react to. Unlike most major inventions, photography had been long and impatiently awaited. The images produced by the camera obscura, a box-like device that used a pinhole or lens to throw an image onto a ground glass screen or a piece of white paper, were already familiar. The device had been much employed by topographical artists like the Italian painter Canaletto in his detailed views of the city of Venice. What was lacking was a way of giving such images permanent form. This was finally achieved by Louis Daguerre, who perfected a way of fixing them on a silvered copper plate. His discovery, the daguerreotype, was announced in 1839. A second and very different process was patented by the British inventor William Henry Talbot in 1841. Talbot's calotype was the first negative to positive process and the direct ancestor of the modern photograph. The calotype was revolutionary in its use of chemically treated paper in which areas hit by light became dark in tone, producing a negative image. This negative, as Talbot called it, could then be used to print multiple positive images on another piece of treated paper. The two processes produced very different results. The daguerreotype was a unique image that reproduced what was in front of the camera lens in minute, unselective detail and could not be duplicated. The calotype could be made in series, and was thus the equivalent of an etching or an engraving. Its general effect was soft-edged and tonal. One of the things that most impressed the original audience for photography was the idea of authenticity. Nature now seemed able to speak for itself, with a minimum of interference. The title Talbot chose for his book, The Pencil of Nature, reflected this feeling. Artists were fascinated by photography because it offered a way of examining the world in much greater detail. They were also afraid of it, because it seemed likely to make their own efforts unnecessary. Photography did indeed make certain kinds of painting obsolete. The daguerreotype virtually did away with the portrait miniature. It also made the whole business of making and owning images democratic. Portraiture, once a luxury for the privileged few, was suddenly well within the reach of many more people. In the long term, photography's impact on the visual arts was far from simple. Because the medium was so prolific, in the sense that it was possible to produce a multitude of images very cheaply, it was soon treated as the poor relation of fine art, rather than its destined successor. Even those artists who were most dependent on photography became reluctant to admit that they made use of it, in case this compromised their professional standing. The rapid technical development of photography, the introduction of lighter and simpler equipment, and of new emulsions that coated photographic plates, film, and paper and enabled images to be made at much faster speeds, had some unanticipated consequences. Scientific experiments made by photographers such as Edward Muybridge and Etienne Jules Méry demonstrated that the movements of both humans and animals differed widely from the way they had been traditionally represented in art.
Artists, often reluctantly, were forced to
accept the evidence provided by the camera, then a candid photography, unposed pictures that were made when the subjects were unaware that their pictures were being taken, confirmed these scientific results, and at the same time, thanks to the radical cropping of images that the camera often imposed, suggested new compositional formats. The accidental effects obtained by candid photographers were soon being copied by artists such as the French painter Degas. TPO 22 Passage 3. The Allende meteorite. Sometime after midnight on February 8, 1969, a large, bright meteor entered Earth's atmosphere and broke into thousands of pieces, plummeted to the ground, and scattered over an area 50 miles long and 10 miles wide in the state of Chihuahua, in Mexico. The first meteorite from this fall was found in the village of Pueblito de Allende. Altogether, roughly 2 tons of meteorite fragments were recovered, all of which bear the name Allende for the location of the first discovery. Individual specimens of Allende are covered with a black, glassy crust that formed when their exteriors melted as they were slowed by Earth's atmosphere. When broken open, Allende stones are revealed to contain an assortment of small, distinctive objects, spherical or irregular in shape and embedded in a dark gray matrix, which were once constituents of the solar nebula, the interstellar cloud of gas and dust out of which our solar system was formed. The Allende meteorite is classified as a chondrite. Chondrites take their name from the Greek word chondros, meaning seed, an allusion to their appearance as rocks containing tiny seeds. These seeds are actually chondrules, millimeter-sized melted droplets of silicate material that were cooled into spheres of glass and crystal. A few chondrules contain grains that survived the melting event, so these enigmatic chondrules must have formed when compact masses of nebular dust were fused at high temperatures, approaching 1700 degrees Celsius, and thin-cooled before these surviving grains could melt. Study of the textures of chondrules confirms that they cooled rather quickly, in times measured in minutes or hours, so the heating events that formed them must have been localized. It seems very unlikely that large portions of the nebula were heated to such extreme temperatures, and huge nebula areas could not possibly have lost heat so fast. Chondrules must have been melted in small pockets of the nebula that were able to lose heat rapidly.
The origin of these peculiar glassy spheres remains an enigma.
Equally perplexing constituents of Allende are the refractory inclusions, irregular white masses that tend to be larger than chondrules. They are composed of minerals uncommon on Earth, all rich in calcium, aluminum, and titanium, the most refractory of the major elements in the nebula. The same minerals that occur in refractory inclusions are believed to be the earliest formed substances to have condensed out of the solar nebula. However, studies of the textures of inclusions reveal that the order in which the minerals appeared in the inclusions varies from inclusion to inclusion, and often does not match the theoretical condensation sequence for those metals. Chondrules and inclusions in Allende are held together by the chondrite matrix, a mixture of fine-grained, mostly silicate minerals that also includes grains of iron metal and iron sulfide. At one time it was thought that these matrix grains might be pristine nebular dust, the sort of stuff from which chondrules and inclusions were made. However, detailed studies of the chondrite matrix suggest that much of it, too, has been formed by condensation or melting in the nebula, although minute amounts of surviving interstellar dust are mixed with the processed materials. All these diverse constituents are aggregated together to form chondritic meteorites, like Allende, that have chemical compositions much like that of the Sun. To compare the compositions of a meteorite and the Sun, it is necessary that we use ratios of elements rather than simply the abundances of atoms. After all, the Sun has many more atoms of any element, say iron, than does a meteorite specimen, but the ratios of iron to silicon in the two kinds of matter might be comparable. The compositional similarity is striking. The major difference is that Allende is depleted in the most volatile elements, like hydrogen, carbon, oxygen, nitrogen, and the noble gases, relative to the Sun. These are the elements that tend to form gases even at very low temperatures. We might think of chondrites as samples of distilled sun, a sort of solar sludge from which only gases have been removed. Since practically all the solar system's mass resides in the Sun, this similarity in chemistry means that chondrites have average solar system composition. Except for the most volatile elements, they are truly lumps of nebular matter, probably similar in composition to the matter from which planets were assembled. TPO-23. TPO-23 Passage 1. Urban climates. The city is an extraordinary processor of mass and energy and has its own metabolism. A daily input of water, food, and energy of various kinds is matched by an output of sewage, solid waste, air pollutants, energy, and materials that have been transformed in some way. The quantities involved are enormous. Many aspects of this energy use affect the atmosphere of a city, particularly in the production of heat. In winter, the heat produced by a city can equal or surpass the amount of heat available from the sun. All the heat that warms a building eventually transfers to the surrounding air, a process that is quickest where houses are poorly insulated. But an automobile produces enough heat to warm an average house in winter, and if a house were perfectly insulated, one adult could also produce more than enough heat to warm it. Therefore, even without any industrial production of heat, an urban area tends to be warmer than the countryside that surrounds it. The burning of fuel, such as by cars, is not the only source of this increased heat. Two other factors contribute to the higher overall temperature in cities. The first is the heat capacity of the materials that constitute the city, which is typically dominated by concrete and asphalt. During the day, heat from the sun can be conducted into these materials and stored, to be released at night. But in the countryside, materials have a significantly lower heat capacity because a vegetative blanket prevents heat from easily flowing into and out of the ground. The second factor is that radiant heat coming into the city from the sun is trapped in two ways: by a continuing series of reflection among the numerous vertical surfaces that buildings present, and by the dust dome, the cloud-like layer of polluted air that most cities produce. Shortwave radiation from the sun passes through the pollution dome more easily than outgoing longwave radiation does. The latter is absorbed by the gaseous pollutants of the dome and re-radiated back to the urban surface. Cities, then, are warmer than the surrounding rural areas, and together they produce a phenomenon known as the urban heat island. Heat islands develop best under particular conditions associated with light winds, but they can form almost any time. The precise configuration of a heat island depends on several factors. For example, the wind can make a heat island stretch in the direction it blows. When a heat island is well developed, variations can be extreme. In winter, busy streets in cities can be 1.7 degrees Celsius warmer than the side streets. Areas near traffic lights can be similarly warmer than the areas between them because of the effect of cars standing in traffic instead of moving. The maximum differences in temperature between neighboring urban and rural environments is called the heat island intensity for that region. In general, the larger the city, the greater its heat island intensity. The actual level of intensity depends on such factors as the physical layout, population density, and productive activities of a metropolis. The surface-atmosphere relationships inside metropolitan areas produce a number of climatic peculiarities. For one thing, the presence or absence of moisture is affected by the special qualities of the urban surface. With much of the built-up landscape impenetrable by water, even gentle rain runs off almost immediately from rooftops, streets, and parking lots. Thus, city surfaces, as well as the air above them, tend to be drier between episodes of rain, with little water available for the cooling process of evaporation. Relative humidities are usually lower. Wind movements are also modified in cities because buildings increase the friction on air flowing around them. This friction tends to slow the speed of winds, making them far less efficient at dispersing pollutants. On the other hand, air turbulence increases because of the effect of skyscrapers on airflow. Rainfall is also increased in cities. The cause appears to be in part greater turbulence in the urban atmosphere as hot air rises from the built-up surface. TPO 23 Passage 2. 17th century Dutch agriculture. Agriculture and fishing formed the primary sector of the economy in the Netherlands since the 17th century. Dutch agriculture was modernized and commercialized. New crops and agricultural techniques raised levels of production so that they were in line with market demands, and cheap grain was imported annually from the Baltic region in large quantities. According to estimates, about 120,000 tons of imported grain fed about 600,000 people, that is about a third of the Dutch population. Importing the grain, which would have been expensive and time-consuming for the Dutch to have produced themselves, kept the price of grain low and thus stimulated individual demand for other foodstuffs and consumer goods. Apart from this, being able to give up labor-intensive grain production freed both the land and the workforce for more productive agricultural divisions. The peasants specialized in livestock husbandry and dairy farming as well as in cultivating industrial crops and fodder crops. Flax, madder, and rape were grown, as were tobacco, hops, and turnips. These products were bought mostly by urban businesses. There was also a demand among urban consumers for dairy products such as butter and cheese, which, in the 16th century, had become more expensive than grain. The high prices encouraged the peasants to improve their animal husbandry techniques. For example, they began feeding their animals indoors in order to raise the milk yield of their cows. In addition to dairy farming and cultivating industrial crops, a third sector of the Dutch economy reflected the way in which agriculture was being modernized: horticulture. In the 16th century, fruit and vegetables were to be found only in gardens belonging to wealthy people. This changed in the early part of the 17th century when horticulture became accepted as an agricultural sector. Whole villages began to cultivate fruit and vegetables. The produce was then transported by water to markets in the cities, where the consumption of fruit and vegetables was no longer restricted to the wealthy. As the demand for agricultural produce from both consumers and industry increased, agricultural land became more valuable and people tried to work the available land more intensively and to reclaim more land from wetlands and lakes. In order to increase production on existing land, the peasants made more use of crop rotation and, in particular, began to apply animal waste to the soil regularly, rather than leaving the fertilization process up to the grazing livestock. For the first time, industrial waste, such as ash from the soap boilers, was collected in the cities and sold in the country as artificial fertilizer. The increased yield and price of land justified reclaiming and draining even more land. The Dutch battle against the sea is legendary. Noorderkwartier in Holland, with its numerous lakes and stretches of water, was particularly suitable for land reclamation, and one of the biggest projects undertaken there was the draining of the Beemster Lake, which began in 1608. The richest merchants in Amsterdam contributed money to reclaim a good 7,100 hectares of land. 43 windmills powered the drainage pumps so that they were able to lease the reclamation to farmers as early as 1612, with the investors receiving annual leasing payments at an interest rate of 17%. Land reclamation continued, and between 1590 and 1665, almost 100,000 hectares were reclaimed from the wetland areas of Holland, Zeeland, and Friesland. However, land reclamation decreased significantly after the middle of the 17th century because the price of agricultural products began to fall, making land reclamation far less profitable in the second part of the century. Dutch agriculture was finally affected by the general agricultural crisis in Europe during the last 2 decades of the 17th century. However, what is astonishing about this is not that Dutch agriculture was affected by critical phenomena such as a decrease in sales and production, but the fact that the crisis appeared only relatively late in Dutch agriculture. In Europe as a whole, the exceptional reduction in the population and the related fall in demand for grain since the beginning of the 17th century had caused the price of agricultural products to fall. Dutch peasants were able to remain unaffected by this crisis for a long time because they had specialized in dairy farming, industrial crops, and horticulture. However, toward the end of the 17th century, they too were overtaken by the general agricultural crisis. TPO 23 Passage 3. Rock art of the Australia Aborigines. Ever since Europeans first explored Australia, people have been trying to understand the ancient rock drawings and carvings created by the Aborigines, the original inhabitants of the continent. Early in the 19th century, encounters with Aboriginal rock art tended to be infrequent and open to speculative interpretation, but since the late 19th century, awareness of the extent and variety of Australian rock art has been growing. In the latter decades of the 20th century, there were intensified efforts to understand and record the abundance of Australian rock art. The systematic study of this art is a relatively new discipline in Australia. Over the past 4 decades, new discoveries have steadily added to the body of knowledge. The most significant data have come from a concentration on 3 major questions. First, what is the age of Australian rock art? Second, what is its stylistic organization, and is it possible to discern a sequence or a pattern of development between styles? Third, is it possible to interpret accurately the subject matter of ancient rock art? Bring to bear all available archaeological techniques and the knowledge of present-day Aboriginal informants? The age of Australia's rock art is constantly being revised, and earlier datings have been proposed as the result of new discoveries. Currently, reliable scientific evidence dates the earliest creation of art on rock surfaces in Australia to somewhere between 30,000 and 50,000 years ago. This in itself is an almost incomprehensible span of generations, and one that makes Australia's rock art the oldest continuous art tradition in the world. Although the remarkable antiquity of Australia's rock art is now established, the sequences and meanings of its images have been widely debated. Since the mid-1970s, a reasonably stable picture has formed of the organization of Australian rock art. In order to create a sense of structure to this picture, researchers have relied on a distinction that still underlies the forms of much indigenous visual culture, a distinction between geometric and figurative elements. Simple geometric repeated patterns, circles, concentric circles, and lines, constitute the iconography of the earliest rock art sites found across Australia. The frequency with which certain simple motifs appear in these oldest sites has led rock art researchers to adopt a descriptive term, the Panoramide style, a label which takes its name from the extensive rock pavements at Panoramide North in desert South Australia, which are covered with motifs pegged into the surface. Certain features of these engravings lead to the conclusion that they are of great age. Geological changes had clearly happened after the designs had been made, and local Aboriginal informants, when first questioned about them, seemed to know nothing of their origins. Furthermore, the designs were covered with desert varnish, a glaze that develops on rock surfaces over thousands of years of exposure to the elements. The simple motifs found at Panoramide are common to many rock art sites across Australia. Indeed, sites with engravings of geometric shapes are also to be found on the island of Tasmania, which was separated from the mainland of the continent some 10,000 years ago. In the 1970s, when the study of Australian archaeology was in an exciting phase of development, with the great antiquity of rock art becoming clear, Leslie Maynard, the archaeologist who coined the phrase Panoramide style, suggested that a sequence could be determined for Australian rock art, in which a geometric style gave way to a simple figurative style, followed by a range of complex figurative styles that, unlike the Pan-Australian geometric tradition, tended to be much greater regional diversity. While accepting that this sequence fits the archaeological profile of those sites, which were occupied continuously over many thousands of years, a number of writers have warned that underlying gasum shanaf such a sequence, a development from the simple and the geometric to the complex and naturalistic, obscures the cultural continuities in Aboriginal Australia, in which geometric symbolism remains fundamentally important. In this context, the simplicity of a geometric motif may be more apparent than real. Motifs of seeming simplicity can encode complex meanings in Aboriginal Australia. And has not 20th century art shown that naturalism does not necessarily follow abstraction in some kind of predetermined sequence? TPO 24. TPO 24 Passage 1. Lake water. Where does the water in a lake come from, and how does water leave it? Water enters a lake from inflowing rivers, from underwater seeps and springs, from overland flow off the surrounding land, and from rain falling directly on the lake's surface. Water leaves a lake via outflowing rivers, by soaking into the bed of the lake, and by evaporation.
So much is obvious. The questions become more complicated when actual volumes of water are considered, how much water enters and leaves by each route.
Discovering the inputs and outputs of rivers is a matter of measuring the discharges of every inflowing and outflowing stream and river. Then exchanges with the atmosphere are calculated by finding the difference between the gains from rain, as measured by rain gauges, and the losses by evaporation, measured with models that correct for the other sources of water loss. For the majority of lakes, certainly those surrounded by forests, input from overland flow is too small to have a noticeable effect. Changes in lake level not explained by river flows plus exchanges with the atmosphere must be due to the net difference between what seeps into the lake from the groundwater and what leaks into the groundwater. Note the word net. Measuring the actual amounts of groundwater seepage into the lake and out of the lake is a much more complicated matter than merely inferring their difference. Once all this information has been gathered, it becomes possible to judge whether a lake's flow is mainly due to its surface inputs and outputs or to
its underground inputs and outputs.
If the former are greater, the lake is a surface water-dominated lake. If the latter, it is a seepage-dominated lake. Occasionally, common sense tells you which of these two possibilities applies. For example, a pond in hilly country that maintains a steady water level all through a dry summer in spite of having no streams flowing into it must obviously be seepage-dominated. Conversely, a pond with a stream flowing in one end and out the other, which dries up when the stream dries up, is clearly surface water-dominated. By whatever means, a lake is constantly gaining water and losing water. Its water does not just sit there, or, anyway, not for long. This raises the matter of a lake's residence time. The residence time is the average length of time that any particular molecule of water remains in the lake, and it is calculated by dividing the volume of water in the lake by the rate at which water leaves the lake. The residence time is an average. The time spent in the lake by a given molecule would depend on the route it took. It might flow through as part of the fastest, most direct current, or it might circle in a backwater for an indefinitely long time.
Residence times vary enormously.
They range from a few days for small lakes up to several hundred years for large ones. Lake Tahoe, in California, has a residence time of 700 years. The residence times for the Great Lakes of North America, namely, Lakes Superior, Michigan, Huron, Erie, and Ontario, are, respectively, 190, 122, 2.5, and 6 years. Lake Erie's is the lowest. Although its area is larger than Lake Ontario's, its volume is less than one-third as great because it is so shallow, less than 20 meters on average.
A given lake's residence time is by no means a fixed quantity.
It depends on the rate at which water enters the lake, and that depends on the rainfall and the evaporation rate.
Climatic change is dramatically affecting the residence times of some lakes in northwestern Ontario, Canada. In the period 1970 to 1986, rainfall in the
area decreased from 1,000 millimeters to 650 millimeters per annum, while above-average temperatures speeded up the evapotranspiration rate. The result has been that the residence time of one of the lakes increased from 5 to 18 years during the study period. The slowing down of water renewal leads to a chain of further consequences. It causes dissolved chemicals to become increasingly concentrated, and this, in turn, has a marked effect on all living things in the lake.
TPO 24 Passage 2. Breathing during sleep.
Of all the physiological differences in human sleep compared with wakefulness that have been discovered in the last decade, changes in respiratory control are most dramatic.
Not only are there differences in the level of the functioning of respiratory systems, there are even changes in how they function.
Movements of the rib cage for breathing are reduced during sleep, making the contractions of the diaphragm more important. Yet because of the physics of lying down, the stomach applies weight against the diaphragm and makes it more difficult for the diaphragm to do its job. However, there are many other changes that affect respiration when asleep. During wakefulness, breathing is controlled by two interacting systems. The first is an automatic, metabolic system whose control is centered in the brainstem. It subconsciously adjusts breathing rate and depth in order to regulate the levels of carbon dioxide and oxygen, and the acid-base ratio in the blood. The second system is the voluntary, behavioral system. Its control center is based in the forebrain, and it regulates breathing for use in speech, singing, sighing, and so on. It is capable of ignoring or overriding the automatic, metabolic system and produces an irregular pattern of breathing. During NREM, breathing becomes deeper and more regular, but there is also a decrease in the breathing rate, resulting in less air being exchanged overall. This occurs because during NREM sleep the automatic, metabolic system has exclusive control over breathing and the body uses less oxygen and produces less carbon dioxide. Also, during sleep the automatic metabolic system is less responsive to carbon dioxide levels and oxygen levels in the blood. Two things result from these changes in breathing control that occur during sleep.
First, there may be a brief cessation or reduction of breathing.
When falling asleep, as the sleeper waxes and wanes between sleep and wakefulness and their differing control mechanisms. Second, once sleep is fully obtained, there is an increase of carbon dioxide and a decrease of oxygen in the blood that persists during NREM. But that is not all that changes. During all phases of sleep, several changes in the air passages have been observed. It takes twice as much effort to breathe during sleep because of greater resistance to airflow in the airways and changes in the efficiency of the muscles used for breathing. Some of the muscles that help keep the upper airway open when breathing tend to become more relaxed during sleep, especially during REM. Without this muscular action, inhaling is like sucking air out of a balloon. The narrow passages tend to collapse. Also, there is a regular cycle of change in resistance between the two sides of the nose. If something blocks the good side, such as congestion from allergies or a cold, then resistance increases dramatically. Coupled with these factors is the loss of the complex interactions among the muscles that can change the route of airflow from nose to mouth.
Other respiratory regulating mechanisms apparently cease functioning during sleep.
For example, during wakefulness there is an immediate, automatic, adaptive increase in breathing effort when inhaling is made more difficult.
This reflexive adjustment is totally absent during NREM sleep. Only after several inadequate breaths under such conditions, resulting in the considerable elevation of carbon dioxide and reduction of oxygen in the blood, is breathing effort adjusted. Finally, the coughing reflex in reaction to irritants in the airway produces not a cough during sleep but a cessation of breathing. If the irritation is severe enough, a sleeping person will arouse, clear the airway, then resume breathing and likely return to sleep.
Additional breathing changes occur during REM sleep that are even more dramatic than the changes that occur during NREM. The amount of air exchanged is even lower in REM than NREM because, although breathing is more rapid in REM, it is also more irregular, with brief episodes of shallow breathing or absence of breathing.
In addition, breathing during REM depends much more on the action of the diaphragm and much less on rib cage action. TPO 24 Passage 3. Moving into pueblos.
In the Mesa Verde area of the ancient North American Southwest, living patterns changed in the 13th century, with large numbers of people moving into large communal dwellings called pueblos, often constructed at the edges of canyons, especially on the sides of cliffs.
Abandoning small extended family households to move into these large pueblos with dozens if not hundreds of other people was probably traumatic. Few of the cultural traditions and rules that today allow us to deal with dense populations existed for these people accustomed to household autonomy and the ability to move around the landscape almost at will. And besides the awkwardness of having to share walls with neighbors, living in aggregated pueblos introduced other problems. For people in cliff dwellings, hauling water, wood, and food to their homes was a major chore. The stress on local resources, especially in the firewood needed for daily cooking and warmth, was particularly intense, and conditions in aggregated pueblos were not very hygienic. Given all the disadvantages of living in aggregated towns, why did people in the 13th century move into these closely packed quarters? For transitions of such suddenness, archaeologists consider either pull factors or push factors. In this case, push explanations dominate. Population growth is considered a particularly influential push. After several generations of population growth, people packed the landscape in densities so high that communal pueblos may have been a necessary outcome. Around Sand Canyon, for example, populations grew from 5-12 people per square kilometer in the 10th century to as many as 30 to 50 by the 1200s. As densities increased, domestic architecture became larger, culminating in crowded pueblos.
Some scholars expand on this idea by emphasizing a corresponding need for arable land to feed growing numbers of people. Construction of small dams, reservoirs, terraces, and field houses indicates that farmers were intensifying their efforts during the 1200s. Competition for good farmland may also have prompted people to bond together to assert rights over the best fields.
Another important push was the onset of the Little Ice Age, a climatic phenomenon that led to cooler temperatures in the northern hemisphere.
Although the height of the Little Ice Age was still around the corner, some evidence suggests that temperatures were falling during the 13th century. The environmental changes associated with this transition are not fully understood, but people living closest to the San Juan Mountains, to the northeast of Mesa Verde, were affected first. Growing food at these elevations is always difficult because of the short growing season. As the Little Ice Age progressed, farmers probably moved their fields to lower elevations, infringing on the lands of other farmers and pushing people together, thus contributing to the aggregations. Archaeologists identify a corresponding shift in populations toward the south and west toward Mesa Verde and away from higher elevations. In the face of all these pushes, people in the Mesa Verde area had yet another reason to move into communal villages: the need for greater cooperation. Sharing and cooperation were almost certainly part of early Puebloan life, even for people living in largely independent single-household residences scattered across the landscape. Archaeologists find that even the most isolated residences during the 11th and 12th centuries obtained some pottery, and probably food, from some distance away, while major ceremonial events were opportunities for sharing food and crafts. Scholars believe that this cooperation allowed people to contend with a patchy environment in which precipitation and other resources varied. Across the landscape, if you produce a lot of food one year, you might trade it for pottery made by a distant ally who was having difficulty with crops, and the next year, the flow of goods might go in the opposite direction. But all of this appears to have changed 13th century. Although the climate remained as unpredictable as ever between one year and the next, it became much less locally diverse. In a bad year for farming, everyone was equally affected. No longer was it helpful to share widely. Instead, the most sensible thing would be for neighbors to combine efforts to produce as much food as possible, and thus aggregated towns were a sensible arrangement. TPO 25. TPO 25 Passage 1. The surface of Mars. The surface of Mars shows a wide range of geologic features, including huge volcanoes, the largest known in the solar system, and extensive impact cratering. 3 very large volcanoes are found on the Tharsis Bulge, an enormous geologic area near Mars's equator. Northwest of Tharsis is the largest volcano of all, Olympus Mons, with a height of 25 kilometers and measuring some 700 kilometers in diameter at its base. The 3 large volcanoes on the Tharsis Bulge are a little smaller, a mere 18 kilometers high. None of these volcanoes was formed as a result of collisions between plates of the Martian crust. There is no plate motion on Mars. Instead, they are shield volcanoes with broad, sloping slides formed by molten rock. All 4 show distinctive lava channels and other flow features similar to those found on shield volcanoes on Earth. Images of the Martian surface reveal many hundreds of volcanoes. Most of the largest volcanoes are associated with the Tharsis Bulge, but many smaller ones are found in the northern plains. The great height of Martian volcanoes is a direct consequence of the planet's low surface gravity. As lava flows and spreads to form a shield volcano, the volcano's eventual height depends on the new mountain's ability to support its own weight. The lower the gravity, the lesser the weight and the greater the height of the mountain. It is no accident that Maxwell Mons on Venus and the Hawaiian shield volcanoes on Earth rise to about the same height above their respective bases. Earth and Venus have similar surface gravity. Mars's surface gravity is only 40% that of Earth, so volcanoes rise roughly 2.5 times as high. Are the Martian shield volcanoes still active? Scientists have no direct evidence for recent or ongoing eruptions, but if these volcanoes were active as recently as 100 million years ago, some of them may still be at least intermittently active. Millions of years, though, may pass between eruptions. Another prominent feature of Mars's surface is cratering. The Mariner spacecraft found that the surface of Mars, as well as that of its 2 moons, is pitted with impact craters formed by meteoroids falling in from space. As on our moon, the smaller craters are often filled with surface matter, mostly dust, confirming that Mars is a dry desert world. However, Martian craters get filled in considerably faster than their lunar counterparts. On the moon, ancient craters less than 100 meters across have been obliterated, primarily by meteoritic erosion. On Mars, there are relatively few craters less than 5 kilometers in diameter. The Martian atmosphere is an efficient erosive agent, with Martian winds transporting dust from place to place and erasing surface features much faster than meteoritic impacts alone can obliterate them. As on the moon, the extent of large impact cratering serves as an age indicator for the Martian surface. Age estimates ranging from 4 billion years for Mars's southern highlands to a few hundred million years in the youngest volcanic areas were obtained in this way. The detailed appearance of Martian impact craters provides an important piece of information about conditions just below the planet's surface. Martian craters are surrounded by ejecta that looks quite different from its lunar counterparts. A comparison of the Copernicus crater on the Moon with the crater Uti on Mars demonstrates the differences. The ejecta surrounding the lunar crater is just what one would expect from an explosion ejecting a large volume of dust, soil, and boulders. However, the ejecta on Mars gives the distinct impression of a liquid that has splashed or flowed out of crater. Geologists think that this fluidized ejecta crater indicates that a layer of permafrost, or water ice, lies just a few meters under the surface. Explosive impacts heated and liquefied the ice, resulting in the fluid appearance of the ejecta. TPO 25 Passage 2. The decline of Venetian shipping. In the late 13th century, northern Italian cities such as Genoa, Florence, and Venice began an economic resurgence that made them into the most important economic centers of Europe. By the 17th century, however, other European powers had taken over, as the Italian cities lost much of their economic might. This decline can be seen clearly in the changes that affected Venetian shipping and trade. First, Venex's intermediary functions in the Adriatic Sea, where it had dominated the business of shipping for other parties, were lost to direct trading. In the 15th century, there was little problem recruiting sailors to row the galleys. Guilds were required to provide rowers, and through a draft system, free citizens served compulsorily when called for. In the early 16th century, the shortage of rowers was not serious because the demand for galleys was limited by a moved-around ships, which required fewer rowers. But the shortage of crews proved to be a greater and greater problem, despite continuous appeal to Venex's tradition of maritime greatness. Even though sailors' wages doubled among the northern Italian cities from 1550 to 1590, this did not elicit an increased supply. The problem in shipping extended to the Arsenale, Venice's huge and powerful shipyard. Timber ran short, and it was necessary to procure it from farther and farther away. In ancient Roman times, the Italian peninsula had great forest of fir preferred for warships, but scarcity was apparent as early as the early 14th century. Arsenale officers first brought timber from the foothills of the Alps, then from north toward Trieste, and finally from across the Adriatic. Private shipbuilders were required to buy their oak abroad. As the costs of shipbuilding rose, Venice clung to its outdated standard while the Dutch were innovation in the lighter and more easily handled ships. The step from buying foreign timber to buying foreign ships was regarded as a short one, especially when complaints were heard in the latter 16th century that the standards and traditions of the Arsenale were running down. Work was stretched out and done poorly. Older workers had been allowed to stop work a half hour before the regular time, and in 1601 younger works left with them. Merchants complained that the privileges reserved for Venetian-built and owned ships were first extended to those Venetians who bought ships from abroad and then to foreign-built and owned vessels. Historian Frederick Lane observes that after the loss of ships in battle in the late 16th century, the shipbuilding industry no longer had the capacity to recover that it had displayed at the start of the century. The conventional explanation for the loss of Venetian dominance in trade is establishment of the Portuguese direct sea route to the east, replacing the overland Silk Road from the Black Sea and the highly profitable Indian Ocean caravan Eastern Mediterranean route to Venice. The Portuguese Vasco da Gama's voyage around southern Africa to India took place at the end of the 15th century, and by 1502 the Trans-Arabian caravan route had been cut off by political unrest. The Venetian Council finally allowed round ships to enter the trade that was previously reserved for merchant galleys, thus reducing transport cost by 1/3. Prices of spices delivered by ship from the eastern Mediterranean came to equal those of spices transported by Portuguese vessels, but the increase in quantity with both routes in operation drove the price far down. Gradually, Venice's role as a storage and distribution center for spices and silk, dyes cotton, and gold decayed, and by the early 17th century Venice had lost its monopoly in markets such as France and southern Germany. Venetian shipping had started to decline from about 1530 before the entry into the Mediterranean of large volumes of Dutch and British shipping and was clearly outclassed by the end of the century. A contemporary of Shakespeare observed that the productivity of Italian shipping had declined, compared with that of the British, because of conservatism and loss of expertise. Moreover, Italian sailors were deserting and emigrating, and captains, no longer recruited from the ranks of nobles, were weak on navigations.
TPO 25 Passage 3. The evolutionary origin of plants.
The evolutionary history of plants has been marked by a series of adaptations. The ancestors of plants were photosynthetic single-celled organisms probably similar to today's algae. Like modern algae, the organisms that gave rise to plants presumably lacked true roots, stems, leaves, and complex reproductive structures such as flowers. All of these features appeared later in the evolutionary history of plants. Of today's different groups of algae, green algae are probably the most similar to ancestral plants. This supposition stems from the close phylogenetic relationship between Titwa groups. DNA comparisons have shown that green algae are plants' closest living relatives. In addition, other lines of evidence support the hypothesis that land plants evolved from ancestral green algae used the same type of chlorophyll and accessory pigments in photosynthesis as do land plants. This would not be true of red and brown algae. Green algae store food as starch, as do land plants, and have cell walls made of cellulose, similar in composition to those of land plants. Again, the good storage and cell wall molecules of red and brown algae are different. Today green algae live mainly in freshwater, suggesting that their early evolutionary history may have occurred in freshwater habitats. If so, the green algae would have been subjected to environmental pressures that resulted in adaptations that enhanced their potential to give rise to land-dwelling or organisms. The environmental conditions of freshwater habitats, unlike those of ocean habitats, are highly variable. Water temperature can fluctuate seasonally or even daily, and changing level of rainfall can lead to fluctuations in the concentration of chemical in the water or even to period in which the aquatic habitat dries up. Ancient freshwater green algae must have evolved features that enable them to withstand extremes of temperature and periods of dryness. These adaptations served their descendant well as they invaded land. The terrestrial world is green now, but it did not start out that way. When plants first made the transition ashore more than 400 million years ago, the land was barren and desolate, inhospitable to life. From a plant's evolutionary viewpoint, however, it was also a land of opportunity, free of competitors and predators and full of carbon dioxide and sunlight. So once natural selection had shaped the adaptations that helped plants overcome the obstacles to terrestrial living, plants prospered and diversified. When plants pioneered the land, they faced a range of challenges posed by terrestrial environments. On land, the supportive buoyancy of water is missing, the plant is no longer bathed in a nutrient solution, and air tends to dry things out. These conditions favored the evolution of the structures that support the body, vessels that transport water and nutrients to all parts of plant, and structures that conserve water. The resulting adaptations to dry land include some structural features that arose early in plant evolution. Now these features are common to virtually all land plant. They include roots or root-like structures, a waxy cuticle that covers the surfaces of leaves and stems and limits the evaporation of water, and pores called stomata in leaves and stems that allow gas exchange but close when water is scarce, thus reducing water loss. Other adaptations occurred later in the transition to terrestrial life and now widespread but not universal among plants. These include conducting vessels that transport water and minerals upward from the roots and that move the photosynthetic products from the leaves to the rest of the plant body, and the stiffening substance lignin, which support the plant body, helping it expose maximum surface area to sunlight.
These adaptations allowed an increasing diversity of plant forms to exploit dry land. Life on land, however, also required new methods of transporting sperm to eggs. Unlike aquatic and marine forms, land plants cannot always rely on water currents to carry their sex cells and disperse their fertilized eggs. So the most successful groups of land plants are those that evolved methods of fertilized sex cell dispersal but are independent of water and structures that protest developing embryos from drying out. Protected embryos and waterless dispersal of sex cells were achieved with the origin of seed plants and the key evolutionary innovations that they introduced: pollen, seeds, and later, flowers and fruits. TPO 26. TPO 26 Passage 1. Energy and the Industrial Revolution. For years, historians have sought to identify crucial elements in the 18th century rise in industry, technology, and economic power known as the Industrial Revolution, and many give prominence to the problem of energy. Until the 18th century, people relied on energy derived from plants as well as animal and human muscle to provide power. Increased efficiency in the use of water and wind helped with such tasks as pumping, milling, or sailing. However, by the 18th century, Great Britain in particular was experiencing an energy shortage. Wood, the primary source of heat for homes and industries and also used in the iron industry as processed charcoal, was diminishing in supply. Great Britain had large amounts of coal, however, there were not yet efficient means by which to produce mechanical energy or to power machinery. This was to occur with progress in the development of the steam engine. In the late 1700s, James Watt designed an efficient and commercially viable steam engine that was soon applied to a variety of industrial uses as it became cheaper to use. The engine helped solve the problem of draining coal mines of groundwater and increased the production of coal needed to power steam engines elsewhere. A rotary engine attached to the steam engine enabled shafts to be turned and machines to be driven, resulting in mills using steam power to spin and weave cotton. Since the steam engine was fired by coal, the large mills did not need to be located by rivers, as had mills that used water-driven machines. The shift to increased mechanization in cotton production is apparent in the import of raw cotton and the sale of cotton goods. Between 1760 and 1850, the amount of raw cotton imported increased 230 times. Production of British cotton goods increased 60-fold, and cotton cloth became Great Britain's most important product, accounting for one-half of all exports. The success of the steam engine resulted in increased demands for coal, and the consequent increase in coal production was made possible as the steam-powered pumps drained water from the ever-deeper coal seams found below the water table. The availability of steam power and the demands for new machines facilitated the transformation of the iron industry. Charcoal, made from wood and thus in limited supply, was replaced with coal-derived coke. As steam-driven bellows came into use for producing of raw iron, impurities were burnt away with the use of coke, producing a high-quality refined iron. Reduced cost was also instrumental in developing steam-powered rolling mills capable of producing finished iron of various shapes and sizes. The resulting boom in the iron industry expanded the annual iron output by more than 170 times between 1740 and 1840, and by the 1850s Great Britain was producing more tons of iron than the rest of the world combined. The developments in the iron industry were in part a response to the demand for more machines and the ever-widening use of higher-quality iron in other industries. Steam power and iron combined to revolutionize transport, which in turn had further implications. Improvements in road construction and sailing had occurred, but shipping heavy freight over land remained expensive, even with the use of rivers and canals wherever possible. Parallel rails had long been used in mining operations to move bigger loads, but horses were still the primary source of power. However, the arrival of the steam engine initiated a complete transformation in rail transportation, entrenching and expanding the Industrial Revolution. As transportation improved, distant and larger markets within the nation could be reached, thereby encouraging the development of larger factories to keep pace with increasing sales. Greater productivity and rising demands provided entrepreneurs with profits that could be reinvested to take advantage of new technologies to further expand capacity, or to seek alternative investment opportunities. Also, the availability of jobs in railway construction attracted many rural laborers accustomed to seasonal and temporary employment.
When the work was completed, many moved to other construction jobs or to factory work in cities and towns, where they became part of an expanding working class.
TPO 26 Passage 2.
Survival of plants and animals in desert conditions. The harsh conditions in deserts are intolerable for most plants and animals. Despite these conditions, however, many varieties of plants and animals have adapted to deserts in a number of ways. Most plant tissues die if their water content falls too low. The nutrients that feed plants are transmitted by water. Water is a raw material in the vital process of photosynthesis, and water regulates the temperature of a plant by its ability to absorb heat, and because water vapor lost to the atmosphere through the leaves helps to lower plant temperatures.
Water controls the volume of plant matter produced.
The distribution of plants within different areas of desert is also controlled by water. Some areas, because of their soil texture, topographical position, or distance from rivers or groundwater, have virtually no water available to plants, whereas others do. The nature of plant life in deserts is also highly dependent on the fact that they have to adapt to the prevailing aridity. There are two general classes of vegetation: long-lived perennials, which may be succulent, and are often dwarfed and woody, and annuals or ephemerals, which have a short life cycle and may form a fairly dense stand immediately after rain.
The ephemeral plants evade drought.
Given a year of favorable precipitation, such plants will develop vigorously and produce large numbers of flowers and fruit.
This replenishes the seed content of the desert soil.
The seeds then lie dormant until the next wet year, when the desert blooms again.
The perennial vegetation adjusts to the aridity by means of various avoidance mechanisms.
Most desert plants are probably best classified as xerophytes. They possess drought-resisting adaptations. Loss of water through the leaves is reduced by means of dense hairs covering waxy leaf surfaces, by the closure of pores during the hottest times to reduce water loss, and by the rolling up or shedding of leaves at the beginning of the dry season. Some xerophytes, the succulents, store water in their structures.
Another way of countering drought is to have a limited amount of mass above ground and to have extensive root networks below ground.
It is not unusual for the roots of some desert perennials to extend downward more than 10 meters. Some plants are woody in type, an adaptation designed to prevent collapse of the plant tissue when water stress produces wilting.
Another class of desert plant is the phreatophyte.
These have adapted to the environment by the development of long taproots that penetrate downward until they approach the assured water supply provided by groundwater. Among these plants are the date palm, tamarisk, and mesquite. They commonly grow near stream channels, springs, or on the margins of lakes.
Animals also have to adapt to desert conditions, and they may do it through two forms of behavioral adaptation: they either escape or retreat.
Escape involves such actions as estivation, a condition of prolonged dormancy, or torpor, during which animals reduce their metabolic rate and body temperature during the hot season or during very dry spells. Seasonal migration is another form of escape, especially for large mammals or birds. The term retreat is applied to the short-term escape behavior of desert animals, and it usually assumes the pattern of a daily rhythm. Birds shelter in nests, rock overhangs, trees, and dense shrubs to avoid the hottest hours of the day, while mammals like the kangaroo rat burrow underground.
Some animals shave behavioral, physiological, and morphological adaptations that enable them to withstand extreme conditions.
For example, the ostrich has plumage that is so constructed that the feathers are long but not too dense. When conditions are hot, the ostrich erects them on its back, thus increasing the thickness of the barrier between solar radiation and the skin. The sparse distribution of the feathers, however, also allows considerable lateral air movement over the skin surface, thereby permitting further heat loss by convection. Furthermore, the birds orient themselves carefully with regard to the sun and gently flap their wings to increase convection cooling.
TPO 26 Passage 3. Sumer and the first cities of the ancient Near East.
The earliest of the city-states of the ancient Near East appeared at the southern end of the Mesopotamian plain, the area between the Tigris and Euphrates rivers in what is now Iraq. It was here that the civilization known as Sumer emerged in its earliest form in the 5th millennium. At first sight, the plain did not appear to be a likely home for a civilization. There were few natural resources, no timber, stone, or metals. Rainfall was limited, and what water there was rushed across the plain in the annual flood of melted snow.
As the plain fell only 20 meters in 500 kilometers, the beds of the rivers shifted constantly.
It was this that made the organization of irrigation, particularly the building of canals to channel and preserve the water, essential. Once this was done and the silt carried down by the rivers was planted, the rewards were rich, 4 to 5 times what rain-fed earth would produce. It was these conditions that allowed an elite to emerge, probably as an organizing class, and to sustain itself through the control of surplus crops. It is difficult to isolate the factors that led to the next development, the emergence of urban settlements. The earliest, that of Eridu, about 4500 BCE, and Uruk, 1,000 years later, center on impressive temple complexes built of mud brick. In some way, the elite had associated themselves with the power of the gods. Uruk, for instance, had 2 patron gods, Anu, the god of the sky and sovereign of all other gods, and Inanna, a goddess of love and war, and there were others, patrons of different cities.
Human beings were at their mercy.
The biblical story of the flood may originate in Sumer. In the earliest version, the gods destroyed the human race because its clamor had been so disturbing to them. It used to be believed that before 3000 BC the political and economic life of the cities was centered on their temples, but it now seems probable that the cities had secular rulers from earliest times. Within the city lived administrators, craftspeople, and merchants. An increasingly sophisticated system of administration led in about 3300 BCE to the appearance of writing. The earliest script was based on logograms, with a symbol being used to express a whole word. The logograms were incised on damp clay tablets with a stylus with a wedge shape at its end. 2,000 logograms have been recorded from these early centuries of writing. A more economical approach was to use a sign to express not a whole word but a single syllable. To take an example, the Sumerian word for head was sag. Whenever a word including a syllable in which the sound sag was to be written, the sign for sag could be used to express that syllable with the remaining syllables of the word expressed by other signs. By 2300 BCE, the number of signs required had been reduced to 600, and the range of words that could be expressed had widened. Texts dealing with economikmeters predominated, as they always had done, but at this point works of theology, literature, history, and law also appeared. Other innovations of the late 4th millennium include the wheel, probably developed first as a more efficient way of making pottery and then transferred to transport. A tablet engraved about 3000 BCE provides the earliest known example from Sumer, a roofed box-like sledge mounted on 4 solid wheels. A major development was the discovery, again about 3000 BCE, that if copper, which had been known in Mesopotamia since about 3500 BCE, was mixed with tin, a much harder metal, bronze, would result. Although copper and stone tools continued to be used, bronze was far more successful in creating sharp edges that could be used as anything from saws and scythes to weapons. The period from 3000 to 1000 BCE, when the use of bronze became widespread, is normally referred to as the Bronze Age.
TPO 27. TPO 27 Passage 1. Crafts in the Ancient Near East. Some of the earliest human civilizations arose in southern Mesopotamia, in what is now southern Iraq, in the 4th millennium BCE.
In the second half of the millennium, in the south around the city of Uruk, there was an enormous escalation in the area occupied by permanent settlements. A large part of that increase took place in Uruk itself, which became a real urban center surrounded by a set of secondary settlements. While population estimates are notoriously unreliable, scholars assume that Uruk inhabitants were able to support themselves from the agricultural production of the fields surrounding the city, which could be reached with a daily commute. But Uruk's dominant size in the entire region, far surpassing that of other settlements, indicates that it was a regional center and a true city.
Indeed, it was the first city in human history.
The vast majority of its population remained active in agriculture, even those people living within the city itself. But a small segment of the urban society started to specialize in non-agricultural tasks as a result of the city's role as a regional center. Within the productive sector, there was a growth of a variety of specialist craftspeople. Early in the Yurok period, the use of undecorated utilitarian pottery was probably the result of specialized mass production. In an early 4th millennium level of the Yana archaeological site at Yurok, a pottery style appears that is most characteristic of this process, the so-called beveled rim bowl. It is a rather shallow bowl that was crudely made in a mold, hence, in only a limited number of standard sizes. For some unknown reason, many were discarded, often still intact, and thousands have been found all over the Near East. The beveled rim bowl is one of the most telling diagnostic finds for identifying an Uruk period site. Of importance is the fact that it was produced rapidly in large amounts, most likely by specialists in a central location. A variety of documentation indicates that certain goods, once made by a family member as one of many duties, were later made by skilled artisans. Certain images depict groups of people, most likely women, involved in weaving textiles, an activity we know from later 3rd millennium texts to have been vital in the economy and to have been centrally administered. Also, a specialized metal-producing workshop may have been excavated in a small area at Uruk. It contained a number of channels lined by a sequence of holes, about 50 centimeters deep, all showing burn marks and filled with ashes. This has been interpreted as the remains of a workshop where molten metal was scooped up from the channel and poured into molds in the holes. Some type of mass production by specialists were involved here. Objects themselves suggest that they were the work of skilled professionals. In the late Uruk period, there first appeared a type of object that remained characteristic for Mesopotamia throughout its entire history, the cylinder seal. This was a small cylinder, usually no more than 3 centimeters high and 2 centimeters in diameter, of shell, bone, faience, or various types of stones, on which a scene was carved into the surface. When rolled over a soft material, primarily the clay of buli, tablets, or clay lumps attached to boxes, jars, or door bolts, the scene would appear in relief, easily legible. The technological knowledge needed to carve it was far superior to that for stamped seals, which had happened in the early Neolithic period. From the first appearance of cylinder seals, the carved scenes could be highly elaborate and refined, indicating the work of specialist stonecutters. Similarly, the late Uruk period shows the first monumental art, relief, and statuary in the round, made with a degree of mastery that only a professional could have produced. TPO 27 Passage 2. The formation of volcanic islands. Earth's surface is not made up of a single sheet of rock that forms a crust but rather a number of tectonic plates that fit closely, like the pieces of a giant jigsaw puzzle. Some plates carry islands or continents, others form the seafloor. All are slowly moving because the plates float on a denser semi-liquid mantle, the layer between the crust and Earth's core. The plates have edges that are spreading ridges, subduction zones, or transform faults. It is at the boundaries between plates that most of Earth's volcanism and earthquake activity occur. Generally speaking, the interiors of plates are geologically uneventful. However, there are exceptions. A glance at a map of the Pacific Ocean reveals that there are many islands far out at sea that are actually volcanoes, many no longer active, some overgrown with coral, that originated from activity at points in the interior of the Pacific Plate that forms the Pacific seafloor. How can volcanic activity occur so far from a plate boundary? The Hawaiian Islands provide a very instructive answer. Like many other island groups, they form a chain. The Hawaiian Islands chain extends northwest from the island of Hawaii. In the 1840s, American geologist James Daly observed that the different Hawaii islands seem to share a similar geologic evolution but are progressively more eroded, and therefore probably older, toward the northwest. Then, in 1963, in the early days of the development of the theory of plate tectonics, Canadian geophysicist Tuzo Wilson realized that this age progression could result if the islands were formed on a surface plate moving over a fixed volcanic source in the interior. Wilson suggested that the long chain of volcanoes stretching northwest from Hawaii is simply the surface expression of a long-lived volcanic source located beneath the tectonic plate in the mantle. Today's most northwest island would have been the first to form. As the plate moved slowly northwest, new volcanic islands would have formed as the plate moved over the volcanic source. The most recent island, Hawaii, would be at the end of the chain and is now over the volcanic source. Although this idea was not immediately accepted, the dating of lavas in the Hawaii chains showed that their ages increase away from the presently active volcano, just as Daly had suggested. Wilson's analysis of these data is now a central part of plate tectonics. Most volcanoes that occur in the interiors of plates are believed to be produced by mantle plumes, columns of molten rock that rise from deep within the mantle.
A volcano remains an active hotspot as long as it is over the plume.
The plumes apparently originate at great depths, perhaps as deep as the boundary between the core and the mantle, and many have been active for a very long time. The oldest volcanoes in the Hawaii Hotspot Trail have ages close to 80 million years. Other islands, including